Hi everybody, welcome back to Chem 161, where we've been chatting all day in the Discord about things like calculus. That button is unavailable to you. What do you mean? So, let me see here. Oops, that's the wrong link. Hold on. I'm going to do this one. So let me go in here really quick. But then, let me just put this on the screen here. So this is what I see. So, oops, that's outside the viewable area. Sorry, let me make sure I get all this. Okay, so this is my screen here. So when you go into the modules, and you click on lab number 4, so it should be this. And then in here, I don't like working inside the little, like, window, so I just hit a button, and I pop up a new window, and then it opens it in a new spot. And it should just be right here. And then just make a copy, and it'll say, make a copy, and you just copy it to your own drive. You do need to be logged into some sort of Google account. If you're not, excuse me, check that, just to make sure that that's working. That's the only thing I can think that's wrong with it, because I haven't heard from anybody else to say, like, oh, it's not working, because then I'd know that I had to hit a button or something was wrong. My other recommendation would be to use a different browser. Like, make sure you're using Chrome or Firefox. Don't use Edge. It's Garbo. Don't use Safari. It's Garbo. I don't know of any other browsers, really. I mean, Chrome and Firefox are Garbo for their own reasons, but they at least work. And if that doesn't work, try a different computer. Just to at least get the file on your drive. That's about all I can recommend, unfortunately. Yeah, try signing into your EVCC account. It shouldn't matter which account you're in, because I have it set to anyone with a link can view. And if you can click on the link to get to it, then you can see it, and you should be able to make your own copy. My best guess is that it doesn't think that you have like a drive or something when you're trying to do that. Okay, so we're going to talk about the last bit of Chapter 3, which is just... this is some review from 140, but we're going to tie in the stuff we learned in 161 with it. So, first we're going to talk about how you make ions, because all Chapter 4 is going to be let's make ionic compounds and then covalent compounds, which aren't ions, but we will use this for the first, like, half of Chapter 4. So, we talked about how to make cations. You take away electrons. You make ions by adding electrons. And how do you do that? Well, the pattern that arises from whenever we add or remove electrons is that we end up being isoelectronic with a noble gas. Now, that is kind of a hand-wavy explanation. This is particularly only true for elements up to calcium. In other words, right before you start hitting the d electrons. We're going to give a more thorough definition in a little bit. But for now, we can make a prediction for most ions using that. Now, I'm immediately giving you an example that isn't up to calcium, but it does work with selenium, and we'll see why in a second. So, looking at selenium here, selenium has 34 electrons. And I want to find the nearest noble gas to selenium. Well, if selenium's element 34, and the noble gases are all those elements in column 8A, the nearest noble gas would be krypton, which is 36. So how do I get selenium to have 36 electrons? Well, if I gave it 2 electrons, it would have 36, right? So the ion that would form would be selenium with 2 extra electrons, electrons being negative. That would be the charge that we form. So that's the ion that we make. Now, what you'll notice about all of the ions that we make is that the valence shell fills up both the s electrons and the p electrons. And this is actually the better rubric that we're going to be using, is that a stable ion has filled s and p valence electrons. So if we were to do this, for example, for barium here, I realize I've written over my sentence here. Barium's nearest noble gas, being element 56, would be xenon, which is element 54. So if I get rid of 2 electrons here, I would then get barium with a 2+ charge, so that it looks like xenon. Which electrons would get removed? Now I gotta clear the text out of the way here. Well, here's what barium would look like. If I get rid of these, now I have a full s and p valence shell. So some elements will ditch their early or their highest energy level electrons to go back to the previous shell to have a full S and P. Now, could you add 6 electrons to barium and fill its p electrons? Well, in this case, you'd have to add 6 and then all the electrons for all the elements in between to get to radon. That's way too many electrons to stick on a barium atom. You get like minus 16. Like, that's not going to happen. Nature's lazy. It wants to take the easiest path. And the easiest path to follow this rule to get a full S and P subshell within a valence layer is just to get rid of those 2 extra. So that's what we're going to do. We're going to try and find out what ions form by making them have full S and P subshells. Now, some elements kind of fall apart when trying to predict what ions they make. So particularly transition metals, lanthanides, and actinides, but also some other elements too, like, for instance, gallium or indium or thallium or lead or things like that. So elements in groups 3A and 4A also have this issue. It's like, how do I get from the center of the periodic table past all these transition metals so that I can get something that has full S and P subshells? And the answer is, well, you just strip away whatever remaining valence electrons are there. Remember how we define valence electrons as stuff that's in the highest N. So, for instance, if I look at iron, and I write out iron's electron configuration, that would be this. So we want it to look like a noble gas, and the noble gas that comes before it would be argon. So I'm going to write that. And it would have 4s2, 3d, and then it's iron. So that'd be 1, 2, 3, 4, 5, 6. And if I note that this is actually 1s2, 2s2. So this is what argon is. If I get rid of these two, the highest level will then be n equals 3. And hey, here's my full sp subshell. What about these d electrons? And we don't care about them. This is all we care about, is getting a full s and p subshell to be present in the valence layer. And we can do that by getting rid of these 2 electrons. So we would predict that a common ion that should form for this would be iron with 2+. Now, are other forms possible? Yeah, you can actually get iron 3+ if you change this down to 5. Because I would have an extra electron here that's paired. I could easily remove that for electron-electron repulsion. So this is easily obtainable too. But this is the one I would expect you to know that you could predict. And the reason for that is once you strip away those s electrons from the 4s shell, the next valence shell down, n equals 3, becomes the layer that has the full s and p subshells. Now, for transition metals, there's going to be all sorts of possibilities based on like things you can do with the electrons. You're only ever going to need to know the common ion that occurs when you get rid of the s electrons in the highest level n that are present. Now, oftentimes that's going to be either 1 or 2 electrons present. So things like copper and silver and gold, you just ditch that 1 valence electron that's available and you get +1. And for almost all cases, that's the ion that forms most commonly. For gold and silver, that's especially true. Copper is oftentimes +2, but +1 is a copper ion that forms. So what I want you to do is, based on that information, get a full S and P subshell for each of these atoms by changing their number of electrons. So either add or remove them, add electrons if they're nonmetals, remove electrons if they're metals, and then create what the common ion is for them. So the first 5 are pretty straightforward. The bottom ones, you should be able to predict a common ion by ditching the valence shell of that metal. And you'll probably get the same charge for most of them. Okay, so give that a shot. Try and write out the ions, then type them in chat the best you can. We'll go over the answers in about 3 minutes or so. See you in a bit. Maya wanted to say hi. I don't think Maya's come around for the evening class in, like, ages. Normally, I've shooed her out of the room enough times during the day that she goes away. All right, one more minute and we'll go over the answers. All right, so let's look at fluorine. We're going to write out these electron configurations and get to a noble gas. So fluorine is 1s2, 2s2, 2p5. I want to get it to be a noble gas configuration with full S and P, so I got to go like that, which means I added one electron to it, so that would be the ion I made. For magnesium, same thing. So 1s2, 2s2, 2p6, 3s2. Adding a lot of electrons would be a lot more work than just doing this. There's my full S and P subshell. I got rid of 2 electrons, so I will get rid of 2 over here. For cesium, I'm just going to write this. I think that's right? Yeah. And then I'm going to get rid of that, and we know that xenon has a full S and P subshell. Easy as that. What about arsenic? Arsenic is argon, 4s2, 3d10, 4p, 1, 2, 3. Here's my valence shell. This is going to be what I want to fill. So I got to get this from 3 to 6, which means I got to go like that, give it 3 electrons, and we're all set. And then tellurium has the electron configuration krypton, 5s2, 4d10, 5p4. There's my valence shell. Let's get that up to 6, and that required 2 extra electrons. There you go. That's how you get the common ion for each of these elements. Now in Chem 140, we just told you this arbitrary rule called the Octet Rule, where we would say, oh, add or remove electrons until you have 8 valence electrons. And that 0 counted as 8. This is the real basis behind the Octet Rule, is that you actually want a full S and P subshell. For nickel here, I've got, let's see here, argon, 4s2, 3d, is it 8? It's 8, yeah. We're going to get rid of these. So the N equals 3 is the valence shell, and that's hidden in here. And we're just going to do that for all these elements. So for copper, we get this. But then you have to remember, oh yeah, that's the D10 or D5 rule. So I take one away from here to add it over to there. So this is what you would expect for copper. Then we can get rid of its 1 electron to do that. And copper 1 is pretty common. Same for cadmium. Cadmium is krypton 5s2, 4d10. We'll just get rid of those. There we go. And we could do this for all of them, really. Manganese is argon, 4s2, 3d5. We'll get rid of these. There you go. And then vanadium, same thing. Goodbye. Goodbye. There you go. Now, can you predict other ions for these? You can. It's not always easy to do. For example, with vanadium, each time you remove an electron from D here, so if this was 3d2 instead, I'd have this. That exists. Why am I crossing out the second last? I'm always crossing out what was the valence shell. So N equals 4 was the highest shell in vanadium. If I get rid of the N equals 4 layer, N equals 3 becomes the new valence shell, and that has full S and P electrons in its valence shell. Remember, that's our goal, is we want to get these underlined ones up here are my full valence shell. Down here, those are contained in this noble gas configuration. If I wrote out the whole thing, so like for nickel, if I did this, so there's nickel. N equals 4 is the highest layer of electrons. If I get rid of it, now N equals 3 is the highest layer of electrons, and there's our full sp subshell. So we would expect that ion to be the one that forms. Got to get at least 2 electrons off of nickel to do that. And you could do that for all of these. Which is why they're all +2, right? Because they all have 2 s electrons. I should say 2 s electrons and not 2s is what I intended there. So the takeaway there is if you're asked to predict a common transition element, predict +2. Unless it's in group, the chromium group, or the copper group, in which case you'd probably predict +1. Alright, if we're going to deal with ions in this class, we first need to differentiate between monatomic ions and then polyatomic ions. Polyatomic ions have covalent bonds going on in them, where all of the elements that are involved share electrons. We'll talk about covalent bonds in Chapter 4. But the number of electrons that are present in all the bonds is enough to produce an ion. And so what that means is that if I add the total number of electrons together, and then I adjust for the charge that's on it, I get the correct amount of electrons. So for example, azide is N3 minus here. This minus affects the number of electrons. So every nitrogen has 7 electrons, right? There's the electron configuration for nitrogen. There's 3, 5, 7 electrons in it. 3 of those together is 21. And then I have to add this in there as an additional electron. So there would be 22 electrons total present in azide as written. Now, in Chapter 4, we're going to ignore core electrons. And what we're going to do is we're going to say, okay, I only care about valence for bonding. So we would say each nitrogen has 5 valence electrons. And this extra electron from this charge is also a valence electron. So the total number of valence electrons in an azide would be a different number, because later on we're going to be counting only valence electrons. So later on in chapter 4, when I say how many valence electrons does it have, don't count all the electrons and then go back to the slide and say, oh, we did it here. Because here I'm just showing you how to count total electrons. All right. Now, the whole point of the last 2 chapters of this class is to talk about the phenomena called bonding. Bonding is how molecules hold themselves together so that you end up with a contiguous sort of cluster that moves together. For example, in water molecules are H2O. Those H's and the O are stuck together. They do not separate without difficulty. And by difficulty, I mean we put energy into it or we do something to chemically make it react. First bond we're going to talk about in chapter 4 is the ionic bond. So ionic bonds form whenever you have anything positively charged next to something that's negatively charged. They attract together because opposite charges attract. Just like the protons in the nucleus attract electrons to them and hold them there, a larger unit with an overall positive charge will attract an overall negative unit towards it. What we're going to do is talk about how to make ionic bonds from elements by shuffling around electrons. Now, because all ionic bonds have to have a cation and an anion in it, ionic compounds must contain metals, because only metals form cations. Because their electron configuration requires us to get rid of stuff to fulfill the requirements of the isoelectronic with a noble gas that we talked about earlier. The other cation that comes up commonly is ammonium. Very important, whenever you see NH4 in a compound, make sure you realize that, oh, that's ionic. I need to pay attention to that. Because it's really easy to say, oh, there's a bunch of N's and H's and other stuff. It must be covalent. Those aren't metals. But ammonium itself acts like an ion. All right. Now, to show this process in action, I'm going to show you the electron transfer for just neutral elements, chlorine, gas, Cl2, and then sodium metal. And I don't know if this is the right video. I want to say that it is, but it might not be. So let me click on it really quick. And it is. That's good. So let's get this over here. Let's capture Lonnie's lab. If you took 140 with me, you've seen Lonnie do his experiment here. Lonnie is a chemist at UC Berkeley, I believe. And I'm not going to have audio here because there's not really much that's going to be added. I'll turn off the closed captioning here too. And so what Lonnie's going to do is he's going to react elemental chlorine with elemental sodium. You could see the chlorine gas in the tube here. It's kind of this yellow hazy material. You can see that when his arm is behind it, you can see the yellow much more clearly. Chlorine gas is a deadly toxin. If you breathe this, you're pretty much hosed. Like, you will not escape with something less severe than, like, ridiculous burns in your lungs. And the reason for that is chlorine gas is pretty unstable. It wants to form an ion because it only has 7 valence electrons. It wants to get that 8th electron in there to be stable. Sodium has the opposite problem. It needs to get rid of its electron. So what Lonnie's doing is he took some sodium out of this container here. It's hard to see, but there's a liquid in there. That liquid is mineral oil, and he just put it in hexane. The hexane is just a wash off the mineral oil. He's going to put it in this scoop. And he's going to put the ladle into the Bunsen burner to heat it up. Now, the heating is just to provide some energy to start the reaction, and also to melt it a little bit so that its surface area increases. That'll give it more places for the chlorine gas to contact when he puts it in the container. You see that it's really hot. If you remember the 140 flame test lab, that's the color for sodium. We're going to put it in there. And then the chlorine gas is going to react with the sodium. And the stuff that's getting expelled is gaseous sodium chloride, which then gets sucked down the fume hood, so Lonnie's not in any danger here. And what's going on here is the sodium metal is passing electrons to the chlorine as it contacts it. When it does that, it gives off light. Then finally, once we've made the sodium and the chlorine ions, chloride ions, I should say, they come together. That's how hot it is, by the way. That ladle is red hot. That gas will slowly condense over time, and you could see down at the bottom it's starting to precipitate out solid sodium chloride. And Lonnie has a sample of it that he prepared in a previous experiment. And this is literally table salt. You can take that you made. In fact, Lonnie's going to do that right now. Don't do this at home. Don't keep an egg in your lab and then eat it. But after the production of sodium chloride, you just use what you've got and then make a snack out of it. I don't think that's enough salt, really, for a boiled egg, but I'm not Lonnie, so there you go. All right, so you've seen visually what observations can be made for the experiment itself, but what can we tell about the actual chemistry that's going on there? What's happening at the atomic level? That's going to look like this. There's the reaction that we're doing. And like we said earlier, I want an electron in this spot. I need this to be a 6, right? Likewise, up here, I need this to go away. So the easiest thing would be, okay, I'm going to take this electron away from sodium. I'm going to add it over here. And when I do that, these are the ions that I get. That 3s is no longer there, and this 3p5 is now a 6. Note that the charges have formed. Then, when I let those two entities get next to each other, they stick together because an ionic bond is what forms out of that. The charges are opposite, and they attract to each other. You get sodium chloride, or table salt. So it's kind of interesting that all the difference between deadly, so this is explosive, and this is super corrosive. This is just delicious. Sodium chloride is totally safe to eat. But sodium metal and chlorine gas, not safe at all. You will die. Or at least regret your choices. If you, put sodium on your tongue, that would be bad. And the reason for this extreme disparity between states is just the electron transfer and the result. When you get a full S and P subshell, as you can see, here's ours for sodium and here's ours for chlorine, you get something that's stable. And so the ions that form for sodium chloride don't have any reason to react anymore. They don't have to pass electrons around. So they're pretty stable. No chemistry will occur in your body. Now, if you're making an ionic compound, why would the sodium metal explode on your tongue? Because sodium metal, again, has this electron configuration. I believe it would actually taste the same, but it has this, and it says, oh, I want to give away my electrons. Who will I give them to? Oh, this is close by. Let me give you electrons. Your tongue doesn't want more electrons. That would disrupt the bonds in your tongue. Also, it would do that very violently, and it would release energy very quickly. So, at the worst, at the least, you would get a severe burn when you did that, because the reaction that you saw in Lonnie's test chamber would be happening in your mouth. And then, worse than that, those extra electrons go somewhere. If you're lucky, it's just the water molecules that are in your tongue, which could then produce hydrogen gas and explode, so that's bad. But even more likely is that something in your tongue, so I don't know, DNA or cell material or anything that's really there, its bonds would be disrupted, and those cells would die, or at the very, even worse, mutate, you get cancer. Probably not from one electron from sodium like that, but, I mean, the way that cancer develops is you get a weird mutation in a cell, and oftentimes that could be from things like light. Not visible light, but like UV light or X-rays or gamma rays or cosmic radiation. Knocking electrons into places they shouldn't be. So don't eat raw sodium metal. Eat sodium chloride. It's yummy and safe. Now, when you make an ionic compound, you always have to have a total charge of 0. If I had something like this, and I allowed this to come towards it, then the overall charge that would be present would just be their sum. And what that means is that there's still enough charge available for something else to be attracted to it and also be included in that group. So we're always going to attract enough ions together so that the sum is 0. Otherwise, this process just keeps happening. You keep attracting more ions together. Now, that's the short version of it to help you remember, oh, that's how I make a formula. I just cancel out all the charges. In reality, it's a little more complicated than that because charges propagate in all directions, and the ions don't care what formula they make. You end up getting what's called a crystal lattice. And do I have a picture of the crystal lattice? Let me see here. Yeah, I'll show you one in a little bit here. But by this basis, we can predict what ions will form what compounds. So with sodium and chlorine, it's easy. I'm going to pass one electron. They both have a charge of 1. They attract each other and cancel the charges out overall. With other substances, it's a little more complicated than that. You have to do a little bit of math. So first, let's predict the ions that would form. So we already know that magnesium makes magnesium plus 2. For iodine, you could predict, oh, I'm one space away from a noble gas, so I'm going to add an electron so it looks like that. And then you'd say, okay, how do I cancel out this plus 2 with these minuses? Well, I need a second one. And then they would all cancel out. So my total charge on both sides would be the same. So the formula that would occur would be Mg, I, and I, or Mgi2. So that's how we predict formulas. First, predict the ions that form using the noble gas configurations that we talked about previously, and then predict the formula. You do this with polyatomic ions, but the ionic charge on a polyatomic ion is already given to you. Now, I gave you the polyatomic ions list, I want to say at the beginning of Chapter 3, or maybe at the beginning of Chapter 6. I forget which one. But you can go look up those ions if you need them, and you will at some point. So, for example, for ammonium and sulfur, sulfur wants to add electrons to it to fill its S&P shells. So, how many will it add? It needs 2 more to fill its p subshell. Now I can create the ionic compound. I have 2 of these, but only 1 of this, so I need to add an additional plus, which comes as an ammonium. So I can then predict the formula. Make sure you put parentheses in there if you need to. Alright, so now what I want you to do, you're going to have to do some looking up stuff if you don't have your polyatomic ions memorized, because you're going to need them now. For the top set, I want you to predict the ionic compound. First, figure out the ions. So, for example, for this first one, sodium would become this, and nitrogen would become that. Make sure you understand why, and then predict the ionic compound that forms once you put enough of them together to balance out the charge. So for this, I need 3 of these to balance out the charges. All right, do that for the other ones. And then down at the bottom, go and look up the ions if you don't know them, and write the formula of the ionic compound for those polyatomic ions. We'll go over the answers in just a little bit. See you then. All right, one more minute. We'll go over the answers here. All right. I was typing there, and I realized, oh, I unmuted my mic to talk, and everyone can hear me type because I have a loud, clicky keyboard. All right, so we'll shove those over there here. Let me zoom this in, and then I'll go like, there we go. All right, so we got cesium and bromine. So we got cesium. Why aren't you writing? Do. Uh-oh. Hold on. What layer am I on? Oh, there it goes. I don't know why it was so slow. Okay. All right, so we got cesium and bromine. So cesium wants to look like xenon. So we're going to get rid of one electron so it does that. So that would be what we form. Bromine wants to gain one electron to look like krypton. So there we go. Those charges balance out. So the formula we would get is cesium bromide. Magnesium wants to look like neon. Get rid of 2 electrons. It can do that. Oxygen wants to gain 2 electrons to look like neon. Same thing here. Those cancel out. We're all set. We can form ions easily. There's no problem here. I don't need to really go over. That's not the right. There we go. So those balance out for the first 3. There we go. So those balance out. That's great. But then what happens if we get 2 ions that don't have the same charge in them? Oh, I'm going to sneeze. Hold on. Maybe. There we go. Oh, excuse me. If I do this, 3 and 2 don't balance out, right? So I'm going to need more of these. Well, that still doesn't balance out. So let me put another one of these down. That still doesn't balance out. Let me put another one of these down. That's the gist of what you got to do to make these balance out. Is you just tack on extra ions. Whichever side needs more, put an ion there. Remember, they come in discrete chunks, so you can't do aluminum in any other charge other than 3+. And then I had 2 of these and 3 of these. So the formula would be, would be that. And then we can do the same thing for my polyatomic ions over here. We'll just leave the answers there to the side. But if I look up ammonium, That's ammonium. And then oxygen would form this ion. I need a second one of these so that they balance out. There you go. Barium would be that. Here's cyanide if you looked it up or know it. I need 2 of these so I can get bacon. No, that's not what that is. This is not bacon, do not eat it. Always put parentheses if you have multiple of those. Can you cross multiply? You can, but if you get a number that can be divided out, I'll show an example where that doesn't quite work in a second here. Let me go through the rest of these examples real quick. So aluminum and chlorate. I'm going to need 3 of these guys, as you can see, because positive 3 and negative 1. AlClO3. 3. Magnesium and nitrate. So nitrate is this. I'll need 2 of them for the minus there. MgNO3, 2. And then finally, calcium and phosphate. This one I need 2 calcium, or 3 calcium actually. We'll write this one out because it's not as straightforward. But same as over here with the aluminum and selenium that you can't see under the screen here. There, you can see it if I do this. Same thing that we did over there. That's how we get those to balance. There you go. Now, an example where just doing the cross multiplication wouldn't work, where you just say, oh, I'm going to just multiply these 2 numbers together. That must be the total charge, right? If I gave you something like this, and like that, because you can do ionic compounds with transition metals, I just have to tell you what the charge is, right? So you might think, oh, I just need 2 of these to do it, and then you'd get this. And that's correct. But if you cross-multiplied these, you would say, oh, well, you would end up with this as your formula instead. And both of those numbers can be divided out by 2. And when you do that, you get the correct answer. So if you cross-multiply, you might get extra numbers that you can divide out. The first one looks weird. Which one are you talking about? Sorry, I missed that in the chat there. Oh, the ammonium one? So remember, ammonium is always NH4+. I need 2 of them to get a positive 2. Oxygen always wants to make -2. And so there's my formula. I have 2 ammonium, sorry, which is why I have parentheses around it. And then I just have one oxygen ion, which would be oxide. Anything, what specifically is weird about it? I try and answer your question. I'm not sure what to point at. But I can circle the charges here, so. Oh no, the 4 is a subscript. Yeah, the charge should be up above it. Cool. Okay, we're all on the same page then. All right, let's go through these last few slides real quick. There's my lattice. So just really quickly to talk about what lattices are. In an ionic compound doesn't propagate charge in one direction. It actually propagates charge in all directions. And so that includes front to back. And so all along these axes, you will get minuses that come in. And this one would be behind it. And then each of those propagates in a direction, and so they would collect charges next to them too. And this would go in the front. It's going to get really complicated to draw these. But this goes in every direction forever and ever and ever and ever and ever. And you get a repeating array of these ions. And so this is called a lattice. So this right here, this is my crystal lattice. Crystal lattice. And so ionic compounds aren't actually little molecules of one cation and one anion floating around. They're just this repeating array that goes forever and ever and ever and ever. And when ions go onto them, they want to fill in faces and make flat surfaces because they can touch the most other ions. If I was to put an ion on the corner, so like if I put a positive over here, I would only be touching this chloride. So this wouldn't be super desirable until other ions came in and started filling in that too to extend the surface. And as a result of that, what you end up seeing are that in ionic compounds, you get these very regular flat edges along the crystal. So if you ever look at a mineral and you see very, very flat, regular surfaces, that tells you, oh, that's an ionic compound. Lots of minerals are just crystalline ionic compounds. In fact, almost all gems are. And that's why you can cut gems like this. It's very easy to do that. Whereas things like gold is a metal. It's just a metal by itself. Metals are really malleable, and you can make them whatever shape you want to. So fool's gold looks like gold, but has a very different texture than gold. Diamonds can make lattices, but diamonds are cut specifically. Well, okay, diamonds can't make lattices because diamonds are actually just carbon, which is covalent. But they're cut to look like other gems, and that's very difficult to do. Buckyball is sort of its own thing. I don't really know how to describe it other than a molecule. But they make covalent network solids, which a little bit different. We'll talk about that maybe a little bit in Chapter 4. What other things do ionic compounds do? So they have very high melting points and boiling points. If you've ever tried to melt sodium chloride in like a pot, you really can't. I do have a video that I can show of this. Of how hot it has to be in order to heat up. No, you're good. How hot it has to be to heat up a ionic compound. So here is table salt. We're going to put table salt into this little cup here. So this test just shows you that when the leads are connected, the light bulb will go on. We're going to add table salt to that, and it's going to appear down here. Not the salt, but like a zoom in of the cup. You should be able to see it down there. And then we're going to heat it with a blowtorch. And the blowtorch heats this to above 800 Fahrenheit. And what ends up happening is the salt begins to melt and it becomes a liquid. And once it reaches the liquid state, the circuit is completed because now you have mobile charges floating around and you can complete the circuit. Then when the torch is removed and this solid cools, it cools fairly rapidly. But until the solid state reoccurs, current can keep flowing. But when it's solid, all those ions are then locked in the lattice because this is recrystallizing down here. And when everything recrystallizes, the light goes out because the circuit is broken. The ions aren't moving anymore. So that demonstrates the conductivity of ionic compounds. Ionic compounds are very conductive if they're molten or if you dissolve them in water. And you did a conductivity test in 140 where we put salt water into a beaker and then you put the conductivity probe and the numbers went up. So you probably remember that. Now, covalent compounds, on the other hand, are very different. And we're not going to really talk too much about covalent bonds yet. We're going to talk about this a lot in Chapter 5 and the end of Chapter 4. But for now, here's what we're going to do to identify covalent compounds. We're going to look at their physical properties. Next slide. Or that there are no metals or ammonium in them. So if you look at a formula and you don't see NH4 and you don't see a metal, it's covalent. What do covalent compounds do? They're just sort of the opposite of ionic compounds. So ionic compounds are conductive and they melt at really high temperature. But molecular compounds have a low melting point and they don't conduct electricity. Dirt is not a metal, but it contains ionic compounds. Mostly like aluminum oxides and stuff like that, and silicon and stuff like that. I'm not a dirt chemist, unfortunately, so I don't really know too much about what's in dirt. But it is mostly just ground up minerals and stuff. There's some common molecular compounds on the screen. You've probably heard of all of these. Of course, you've heard of CO2 and oxygen. There's the formula for sugar. Now, even though it's molecular, you can still make it a solid and put it into a crystal shape, but it's not going to form a lattice. In fact, if you look at a sugar crystal under a microscope really close, you won't see individual molecules, but what you'll see is that the crystals that are there are super irregular. They're like bloppy and odd shaped, whereas salt crystals are very, very square and cubic-like. So for this last slide here, before we take our break, I want you to tell me, is it molecular or ionic, just based on the formula? Type your answers in the chat. We'll go over the answers in like 1 minute or so, and then we'll take our break, because we're due for one. All right, do we have the answers? Oops. Hint. All right, so for these, it's really just a matter of find the metals. So there's a metal, there's a metal. And then if you have ammonia, find that too. So these would be ionic. And then anything that isn't ionic will be covalent for our class. All right. Any questions about ionic versus molecular? You'll have to just be able to differentiate between them on the quiz. All right. Guess what? I know, this is the part we've all been waiting for, right? It's over! That's it. We're done with Chapter 3 forever. Not really forever. I mean, it will come back on the quiz. That's it, we're done! Hooray! Go take a break. And celebrate that Chapter 3 is behind us. All right, we're back. I can see everybody's scores here. Yeah, double check. Check in the. I don't know if you can see the thing called that says grades. Yeah, you should be able to click on grades, and it should say Lab Worksheet 3. Yeah, I uploaded scores today for everybody that I got one from, and it was all in there, and it looks like it's visible. Yeah, I could hide it again. I don't want to do that. Yeah, I was just doing world map themes from Final Fantasy this week, and then I had that track. And I was like, well, it's the Final Fantasy VII world map theme. I could throw in a Final Fantasy VII song from the remake, which is so good. You should play it if you have it. All right, chapter 4. What do I say about chapter 4? This is more or less the last chapter. There's like 20 slides on chapter 5, which I don't know why chapter 5 is such a tiny chapter. We're going to do that on the last day. That'll be week 10, Wednesday. That'll be the last thing we do. Chapter 4 has a lot of slides, but it's a lot simpler than quantum mechanics, and you've actually done a lot of this before. So, like, all the way up to about 4.5 here is going to be old hat. So you've seen all this stuff. We're going to cruise right on through all of that. And, yeah. So, I'm not a DJ, but I know a lot of DJs, it turns out. A lot of my friends became DJs for some reason. One was an aerospace engineer, and then, well, I think he's still an aerospace engineer, but he's also a DJ. So. All right, let's talk about bonding in a little bit more detail. So, the first thing that we're going to talk about here is in the last section at the very end, we talked about how, ionic compounds have high melting points, but molecular compounds typically have low melting points. Ionic compounds are conductive, but molecular compounds aren't. There must be some difference between those, and the difference is in their bonding. And so for this last chapter that we're going to talk about, and chapter 5, which I'm going to loop into here, we're going to talk about chemical bonds. A chemical bond is any interaction between two atoms or ions that holds them together. Now, the way that we do this is entirely through electrons. So electrons are the key to chemistry. Like we said before with Coulomb's law, it's the secret to chemistry. Coulomb's law explains everything in quantum mechanics, more or less. And then we can apply what we've learned in quantum mechanics to bonding. We're going to shuffle electrons around in new and interesting ways to describe how bonding works. First, we're going to do ionic, and then we're going to do covalent. So the first few sections will talk about ionic. So we've already shown this picture. We've already discussed, I put the positive thing next to the negative thing, and you get a bond. Cool. That's not super exciting right now, but we're going to talk about that in more detail. Here's our lattice again. Now, if I want to break the lattice apart, that doesn't mean that I just break apart this interaction between Na and Cl. I have to break apart every interaction between Na and Cl. And you can see that there are a lot of those here. And I'm just only drawing, I've only drawn 8. There are tons of them in just this little structure. And this structure is only a 6 by 6 by 6 cube. In a regular ionic compound, you'd have quintillions of ions all stuck together, and you'd have to rip every single one of those apart. And so the amount of energy to do that borders on absurd. So this is a large number for energy. To dissociate 1 mole of ions and to make them a gas, which would be completely separating them out, requires 769 kilojoules of energy just for sodium chloride. Now, how do we contextualize that number? Like, how much energy does that require? We're not really talking about thermodynamics in this class, but I can give you a rough approximation that a kilojoule, so 1 kilojoule, will heat 1 liter of water by 1 degree Celsius. Actually, no, I'm sorry, that's wrong. Sorry. That's 1 calorie, 1 kilocalorie, so I'm going to round it to 1 sig fig. We're just going to write 4 kilojoules. It's actually 4.184, but So 4 kilojoules will heat 1 liter of water by 1 degree Celsius. So if you have a liter of water and you get it to boiling, to heat it to 100 degrees Celsius would take 400. So if you started at 0 and heated it all the way to 100, that's still not enough energy to dissociate. 1 mole, which would be a little teeny tiny amount of salt. 1 mole of salt is only about 55 grams or so. So that's a lot of energy to tear all of this apart. Now, excuse me. In our discussion of ionic compounds, I'm going to use the term formula unit. What a formula unit is, one pairing for our quote-unquote molecule, or in other words, whatever the formula says. So the formula unit for NaCl would be an individual sodium and an individual chloride ion. Now, you can't use molecule for this, because if I asked you, where's the molecule, and I said circle it, you can't, really, because there's no independent molecule in the structure. Because they're all attracted to each other, right? So we can't use that term here. So when we do math with this in 162, and I ask you how many formula units are in this many grams, and you start doing stoichiometry with it, that's what the term formula unit means. Colloquially, you can think of it as a molecule, but it's not really a molecule. We're going to talk about molecules later on. All right. And then covalent bonds don't make ions. Instead of making 2 ions, so for example, if I had fluorine here, fluorine with its 7 electrons in the valence shell, so if I draw out its electron configuration, remember, I want to get this to be 6, right? If I do that with another fluorine, which also has the same number of valence electrons available, I can't move 1 electron from one to the other, because this will just get this further away, even though this will work. So this one will be fine, but then this one's ruined, right? I'm getting further away from having a full S and P subshell. So 2 nonmetals bonding to each other cannot accomplish what ions do. They shuffle electrons around because some of the atoms want to get rid of them. Metals don't want electrons to get to their full S and P subshell in the previous valence layer. Nonmetals need to come up with something different. And so what we will do when we get to talking about covalent bonds is show how that works with diagrams and pictures to do that. Now, in order for covalent bonds to form, their electrons live in orbitals. So, for example, I have H2 here. Remember that H2 is just this, right? And if I was to draw the orbital for a 1s orbital, it would just look like this. It's a circle, right? In that circle somewhere is your electron. So in this diagram over here, I have H and H. Actually, you know what I'll do? I'll draw the other one upside down so I can pair them. Now, obviously, they're not paired because they're too far apart. They don't see each other. So then when I come over here, I want to try and squeeze them together to pair them into the same orbital. And where that happens is where the orbitals intersect. We're going to talk about this in a lot more detail in Chapter 5, but here there's a region where both of my orbitals overlap. And my 2 electrons that I'm going to use for bonding will tend to be in there. And what ends up happening in a covalent bond is you get a system that looks kind of like this. I'm going to draw it down here. So here's my hydrogen atom. And then I have my electrons, which have paired. And then here's my other hydrogen atom. And what we have going on here is we have an attraction between the positives and the negatives. And even though the negatives themselves repel, they're paired by opposite spins, so that repulsion is somewhat nullified. The overall result is that the electrons spend most of their time in the middle there, in this overlapping region. And the result is you get a bond, and that's a covalent bond. So that's what it looks like in terms of the electronic structure and the picture of the orbitals and all that stuff we talked about in Chapter 3. Now you might think, oh, okay, well, why not just shove these closer together so that the orbitals are just perfectly on top of each other, right? Then the electrons have all sorts of space to work with. And the issue that you get into there is that at some point, the two nuclei are just too close to each other. And they repel. So this part of the graph here is showing, oh, it requires energy to push my two nuclei or two atoms this close together. But if I get them this distance apart, then they have the optimal attraction. And so this is what the bond length would be between these two atoms. So in ionic compounds, you just bonk the two orbitals so that they're adjacent. You don't need to overlap them because the charges do that for you. Or the opposite charges hold them together for you. But in covalent compounds, you got to squeeze everything together so that you get orbital overlap. We're going to talk about that in more detail in Chapter 5. All right. Now, the end result for covalent compounds is that if I have a covalent compound like water here, and we'll talk about what all of this that I just drew means probably tomorrow. This water molecule is essentially independent from other water molecules. And the reason they're independent is because I don't have any bonds holding them together. So these lines right here, these are my bonds. But there's nothing in this space that holds these two atoms together, these two H's, or this H and this O, or whatever. And so I get all of these independent little things that are themselves floating around and moving in whichever way that they want to. And these independent entities are what we call molecules. So covalent compounds form discrete molecules that don't stick to each other through bonding. Now, do these molecules attract to each other in some way? So are these water molecules attracted to each other somehow? Well, if I was going to make a solid out of them, they would have to be, right? Otherwise, they just all fly in opposite directions and become a gas. So there must be some attraction that holds molecules together, and there is. We're going to talk about that at the very end of Chapter 4, which is actually a small snippet from Chapter 10 that we do in this class so that if you're taking bio, you can go to the next bio class because you've seen intermolecular forces. We'll talk about that at the end of this chapter. But for now, just assume that molecules don't stick to each other and there's nothing that connects them. Because for our purposes, that'll be okay at present. So the first property we're going to talk about that governs how bonding occurs is called electronegativity. Now, some elements tend to give their electrons to other elements. And other elements just sort of say, well, meet me halfway, we'll share them. And it'd be really cool if we had a numeric value that sort of dictated, okay, this is when ionic will occur, and this is when covalent will occur. And hey, we do. It's called electronegativity. So electronegativity is going to be a numeric value that judges how much an atom wants to give electrons away versus how much it wants to take electrons or versus how much it doesn't care. Now, if we have the two extremes here, where I just transfer electrons on one side, and over here, we just share them, if these are two extremes, what happens in the middle? The answer is that there's sort of both. We don't really transfer our electrons, but we share them unequally. So maybe, oops, that's not where I thought my cursor was. Maybe this atom shares its electrons more than this one does. And so that middle region is going to lead to a bunch of really interesting properties that we're going to focus our study on. And it's sort of going to be the bridge between ionic and covalent. Because as binary as we are trying to set the system up to be, reality isn't quite so discrete. There's going to be some molecules that exhibit properties of both ionic and covalent to some degree. Like water. Water's a really good example of that. Water is molecular, it's independent, but it has very interesting properties in terms of electronics that make all sorts of really cool stuff happen. Now, what's the easiest way to get this uneven sharing? Well, electrons will be shared unevenly if you use different atoms to make a bond. In other words, if I put two H atoms together, they're exactly the same. They will share exactly the same. But if I put H with some other atom, like, say, chlorine or fluorine or something like that, something different will happen. One of the atoms will want the electrons more than the other. And it's our job to figure out how that works and to try and describe it as best as we can. So let's look at chlorine. I've drawn on the board a Lewis structure, which if you took 140, you probably remember this. All the dots represent electrons, and then that line that connects them is a pair of electrons that is shared. What we're going to do is we're going to think of these electrons in the middle here as sort of a tug-of-war situation. Like, imagine the electrons are a rope, and then the Cl on the left is trying to pull the electrons towards it because chlorine has a nucleus and the electrons would be attracted to it. And the chlorine on the right is doing the exact same thing. But they're both chlorine. They both have 17 protons. They both have X number of electrons in their core shell. And then there's these two electrons that are in the bonded area. Who would pull harder? Well, since they're both chlorine and they both have exactly the same properties to them because they're both the same atom, the electrons would be shared equally. So if I had to put like an arrow to say where would the electrons be most of the time, I would say, oh, right in the middle, roughly 50-50. Another way to say that would be that the electron density is constant. Now, what the hell does that mean? Remember that electrons live in orbitals, right? So my orbitals, I'm just going to draw a generic s orbital here for now. Most of my electrons would be in this region as opposed to, say, over there or over there. And those the overlap would be right in the middle as opposed to shuffled to one side. Now let's look at an example that would be uneven. Hydrogen only has one proton, so it's not going to be able to pull all of these electrons toward it. It doesn't have enough ability to do that. So in HCl, my electrons would be closer to the Cl side. However, they don't get all the way to Cl. If they did, this would happen. And I'd have an ionic compound. But that's not what we observe. We observe HCl has properties of a covalent compound, particularly if you look at it in the gas phase. So if I was to draw just like a generic blob diagram, so something like this, if I were to just draw, okay, this is the region where my electrons live, I would say, oh, most of my electrons are on this side of the molecule, and they're not over here as much. They're mostly over here. Later on, we're going to represent that with something that looks like this, or something that looks like this. That's supposed to be a delta, a lowercase delta. to represent partial charges, or the electrons are more on the chlorine side than the hydrogen side. So it's kind of like I have half a charge, or a third of a charge, or something like that. Now, why does this happen? We just mentioned it. So if I have more protons in the nucleus, I am more able to pull electrons toward myself. So having a higher Z or Z effective represents the ability to pull electrons towards you more effectively. Hydrogen only has Z effective of 1. Chlorine has Z effective of 7+. Chlorine's going to pull the electrons tighter to itself. We can also talk about electron affinity. Atoms with higher electron affinity will want electrons to be pulled towards their nucleus more. Electron affinity is a function of Z effective. So it's sort of like saying that the sky is blue because you see it and it's blue. But it is a property that we can reference. Oh, what has the higher electron affinity? That one does, so that atom will pull electrons towards itself. Now, probably the last thing you want to do is go dig back into quantum mechanics and start calculating Z effectives and electron affinities. Well, fortunately, this guy did all this work for us. This is Linus Pauling, and he went insane. That's how I like to introduce Linus Pauling. He's a brilliant chemist who did all of these calculations that combined Z effective, electron affinity, ionization energy, quantum mechanics, and all that, and he condensed all of it down into this nice little number that we assign every atom called electronegativity. And then after that, he went nuts. I mean, that's what happens when you get old. I'm looking forward to it myself. All right. The formal definition of electronegativity is how well does an atom pull electrons towards itself through bonds? So if it was playing in tug of war, how likely will it be to win tug of war? And not just that, how soundly will it trounce its opponent? Because that's going to dictate what type of bond we have. If the electronegativity difference is tiny, the electrons end up shared because nobody wins. They just stay in the middle. If the electronegativity difference is big, the electrons get pulled towards the atom that has the higher electronegativity. And if it's big enough, the atom with the higher electronegativity just keeps the electrons, and you get an ionic bond. What do we measure electronegativity between? We scale them between 0 and 4. 4 is the highest and is the most electronegative. 0 is the lowest and is the least electronegative. Now, like we said, electron affinity is used to calculate electronegativity here. So make sure that you don't get these two terms mixed up because they are different, but they are related. We're more or less done with electron affinity. We're going to just talk about electronegativity here. On the next slide, I have a chart. This chart shows you all the electronegativity numbers for every element on the periodic table that is not a lanthanide or actinide. Well, I mean, it kind of does. All the lanthanides and actinides kind of have the same. Oh, these are actinides. Okay, I didn't realize that they were there. Okay, so yeah, this shows every element up to nobelium. Cool. And they more or less all have the same electronegativity in there because they're roughly in the same part of the periodic table. You'll notice that there's a general trend for electronegativity on the table. As you go from left to right, the numbers get bigger. And as you go top to bottom, the numbers get smaller. That means that the highest electronegativity element must be in the top right, and that's fluorine. Fluorine is the highest electronegativity, and not by much, it's by a long shot. If you go up against fluorine in the electron tug of war, you lose, unless you are also fluorine, in which case you tie. Every element loses to fluorine. Likewise, every element beats francium. Sorry, francium. Sucks to be you. Hope you didn't like your electrons. Now, why do these trends do what they do? Well, as you go from left to right, Z effective increases, right? And if Z effective increases, electrons are pulled towards the nucleus more effectively. As you go down, the electrons get further away because N increases, right? And if those electrons are further from the nucleus, they're easier to yeet right off, right? Yes, I said the word yeet. And there you go. We've used quantum mechanics. We spent 4 weeks talking about quantum mechanics so I could summarize it in 20 seconds, right? God damn it. I hate quantum mechanics. Ugh. Said every student ever. I think it's super cool, but I totally understand that, like, oh man, we did all of that so you could just say that. Yeah. Now, there are some interesting weird things in the middle of the periodic table. This section that I've circled is called the noble metals. We'll highlight them. The noble metals have a higher than normal electronegativity compared to the elements that are around them. This is kind of a weird phenomenon. This has to do with atomic size. These atoms get particularly small relative to the elements that are around them. And what ends up happening is that those electrons get slightly harder to take. And as a result, what we observe is that these elements tend to be particularly corrosion resistant. For instance, you might have gold jewelry and notice that, like, man, gold just stays shiny and pretty no matter what happens to it. Same with platinum. Platinum is really resistant to corrosion. That's why we use these materials in things like electronics, or maybe in a spark plug. In like the spark plug in an engine for a vehicle, sometimes the tips might be coated in platinum. And the reason for that is because platinum is super corrosion resistant. And that's important because you're going to be putting it in a situation where there's lots of oxygen, heat, fuel, and conditions that would not be easy to be unreactive in, we'll say. And platinum holds up. Because if your spark plug becomes unreactive and it corrodes over the surface, you couldn't conduct a charge between the electrodes, and then your engine wouldn't fire. And that's obviously bad. So some elements are capable of resisting electron transfer. And those elements tend to be in this region right here. So there's our summary of our trends. And again, electronegativity tries to lump the concepts of all of the quantum mechanics stuff that we talked about into this nice, convenient number. Yeah, I'd believe that. Platinum is really good for that. I don't know what metal is used for, like, the cheapo stuff that, like, I would get, because, like, a platinum tipped spark plug is probably way, way, way more expensive by, like, orders of magnitude, I would say. Instead of paying $10, you'd pay $100 or something. Yeah, that's really all I know about that. Oh, do we use copper? That makes sense. Okay. Copper's really conductive. The next element I would have guessed would have been silver, because silver's not super abundant, but it does have a high electronegativity. Copper is even more abundant. Oh, it has the same electronegativity. Okay. Copper will eventually corrode. But copper is pretty good at being corrosion resistant. We use copper for all of our electrical wires because it's more or less the same properties as silver. Oh, so it is an order of magnitude, but I thought spark plugs were much more expensive than they were. Okay. This is my, what is it, Arrested Development? How much could a banana cost? $10 sort of situation. Like, I don't know how much a spark plug costs. I just sign off on the bill when I go take my car to the shop. Okay. So when we come back tomorrow on Tuesday, we're going to talk about trends in electronegativity. So really right now, all you need to know is that electronegativity is a phenomenon that exists, and it's represented by a number, and it sums together everything we talked about in Chapter 3 and distills it down into this nice little frustrating number that makes you wonder what exactly we spent the last 3 weeks of our lives doing. But it's important enough that we cover it in great detail because we're going to use those topics later when we talk about chapters 4 and 5. It's the end of chapter 3, so what that means is that quiz chapter 3, we'll say, will be going up tonight. You'll have a week to do it. Quiz number 3 is a doozy. It covers the entirety of chapter 3, so make sure you're ready. And remember, you do get to take it twice. Have all your information sort of like in the mise en place sort of setup, like have everything handy and just be able to refer to it if you need to. You only get 35 minutes, so... Or maybe it's not 35. I think it's 45 for this class. Whatever it is, that's the time that you get. But yeah. We're going to continue more Chapter 4 tomorrow, and we'll see you for that. There is a lab worksheet due tomorrow. Make sure you get that in, too. Have a good night. We'll see you for Chapter 4.